Hello, my name is Sören van der Waal, and in this session I'm going to present to you our results on the complexity of multi-pushdown games. Now first have a look at the computational model. Multi-pushdown systems model concurrent recursive programs, which are multiple threads that communicate via some shared memory. Every thread can recursively call functions, and eventually they may return. The multi-pushdown system models this by having a stack for each thread that captures the call structure of that thread. And then when the memory and the program locations of the threads is abstracted by a finite state split. After that, we can translate the programs into transition relations, which act only on a single stack each. Now, a computation in our model is a sequence of transitions, which is an interleaving of the different threads computing their transitions. In our example computation, we start at the left with the stack contents on the right. The first transition may be an internal transition, so it does not act on the stack at all. It simply modifies the states. The second transition might be a popping transition, where we remove the top of the first stack. And then the third transition may be a pushing transition, which introduces a new symbol to the second stack. After that, we may have another internal transition, maybe another popping transition, and maybe another internal transition. That concludes our computational model, multi-pushdown system, where we have a state space, we have multiple stacks, and for every stack, we have a transition relation that manipulates that stack. As with many concurrent programming models, we have no decidable reachability problem, so instead we are looking at bounded computations. And the most prominent bounded computation is probably context boundedness, where we identify consecutively executed transitions on the same stack as one context. For example, here we have the first two transitions executing on stack 1, and they form the first context of this computation. Then the context is always switching, so we only have the first context, which consists of more than one transition. And when we bound the context, the number of contexts that may occur in a computation, we actually re-achieve decidability in X time. Now, phase boundedness is another approximation which is possible, and they kind of generalize the idea of a context. A phase-bounded computation is interested in when a popping transition happens, and whenever the stack changes that does popping transitions, a new phase begins. So in our example, we have the first phase when stack 1 pops, and after that there are no popping transitions. And then when we have the next popping transition, it acts on stack 2, so we have a new phase that begins here because it is not the same stack as stack 1. Also here we re-achieve decidability in 2x time. And the last under approximation of multi-pushdown systems are ordered multi-pushdown systems, where we have an ordering on the stacks, and a popping transition may only occur if all stacks of lower order are already empty. So what does it mean? Let's have an example computation where we start with a popping transition on stack 1. This is okay because there are no stacks lower in order than stack 1. Now we have a pushing transition and a popping transition on stack 2, and the second popping transition is only possible because the first stack is actually empty. And then we have another pushing transition on stack 1 and another popping transition on stack 1. Again, stack 1 has no stacks lower of order. Now, if you would assume that the last transition is not a popping transition on stack 1, but rather on stack 2, we will see that this is not an ordered computation anymore. This last popping transition cannot be executed, because stack 1 still has elements on it. Also here we re-achieve decidability in 2x time. Now what we considered were multi-pushdown games. Games on a computational model are often needed to be solved when we are considering branching time logics or when we are looking at synthesis problems. Now a multi-pushdown game has two players, Eve and Anna, and the state space of the multi-pushdown system is divided, and each player owns one partition of the state space. Also, every state has a priority, which is important for the winning condition. The game is then played on the configuration graph of the multi-pushdown system, where every node consists of a configuration, so a state and stack contents, and the edges in between are the other transitions of the multi-pushdown system. We start in the initial configuration with empty steps, and because in this example it is the state belongs to Eve, Eve will be the first one to make a move. And making a move just means choosing the next transition. So Eve will choose a transition. Again, the next configuration is owned by Eve, so again Eve will choose the next transition, and so on. And now we have a configuration owned by Anna, so Anna will be the one to make the next move, and she will choose a transition. Doing this infinitely long, we will obtain an infinite sequence of configurations. And then we can determine the winner by looking at the maximal infinitely often occurring priority. And we let Eve win if it is even. Now that is a parity winning condition. Now when we are trying to solve a game, we are actually trying to find a winning strategy for one of the players. And in our case, it will be Eve. And a winning strategy is nothing but a subgraph of our configuration graph where every node that belongs to Eve has already a predetermined move to make. So when we look at this tree, it has, for every configuration that belongs to Eve, only one successor. And for every configuration that belongs to Anna, there are still all the successors possible. And the strategy is then winning if all the plays that are possible within the strategy are winning for Eve. Now, of course, finding a winning strategy is also undecidable. And we have to look at bounded multi-pushdown games. So here are our results for the bounds that we just currently found, which we just saw. For k-stack ordered multi-pushdown systems and k-phase multi-pushdown systems, we are able to obtain a kx upper bound, and for k-context bounded multi-pushdown systems, we were able to spare even 2 further exponents. Now this is quite expensive, and when we look at having the parameter k as part in the input, we see that immediately the complexity jumps to non-elementary. However, we are not the first ones who are working in this field. There has been an upper bound already for k-phase multi-pushdown systems, which operates in a similar fashion as ours. However, we spotted a small bug, and we were able to carry it over to ordered multi-pushdown systems. Don't be confused. The k-context upper bound is of course existent because phases are a generalization of contexts. Okay, so let's jump into our upper bound. The idea is that we have this gigantic configuration graph, and it is infinite only because there are stacks within the configurations. So what we want to do instead is we want to remove the infinity of the stacks and only store the top of stack symbol of each stack within our configuration. And then we want to simulate the original game as if nothing is different. However, this is of course not the case, because whenever we run into a popping situation, we cannot simulate this. We don't have the next top of stack symbol which would come, because we did not store it. So what happens instead, we will make one of the players win or lose in this situation. And to do this faithfully, we will have to store some additional information about the current state in the position. Another thing that our finite state has to be able to do is to simulate plays that actually go beyond a popping situation. So also there we will have what I call a skipping mechanism, where we can skip certain sequences in the play and then continue the play after a popping situation. Okay, how does summarization work? And I want to do this first for single stack pushdown systems, so we can understand this, and then we can carry the ideas over to multi-pushdown systems. Let's start with a strategy for Eve in a single stack pushdown game. It is a tree, of course, and every branch in the tree is a play that is conformed to a strategy. Let's look at a certain push-pop pair in this fixed play, where push-pop pair means the pushed symbol is popped by the corresponding pop later. Okay, the idea of summarization is to look at this sequence and understand the effect of the sequence, one, on the configuration, and secondly, on the winning condition of the game. And when we have done this, we want to store it in a summary for this sequence. And the finite game shall then be able to skip from the pushing situation to after the popping situation, looking at the summary, making the effect visible to the game, and continue playing the game, the finite game, as if the sequence was played, even though we just skipped it. Okay, let's identify what a reasonable summary is for a single stack pushdown game. First, let us look at the effect on the configuration. Because this is a push-pop pair, the stack contents have to be equal. There's no other way. So the only change in the configuration is actually the state that changes. So what we add into our summary is the state of the game after the pop. Now, the effect on the winning condition, however, is the maximal priority that we have seen during the play, because the winning condition is interested in the infinitely often seen priorities and only in the maximum of those. So we can look at, so we can understand the effect of the sequence at the maximal priority that we have seen during the sequence. So now when we want to play the finite game, we can actually skip. So let's have an idea, actually skip. However, we are looking at a game, and what we have in front of us is a strategy for Eve. So when the game eventually might visit the push that we have drawn here, there's not only a single play and not only the fixed play that we have here, but there are many plays that can occur after the push. And many of them could potentially pop the symbol that was just pushed. And of course, the sequences between the push and the different pops might be different ones. However, what we notice immediately is that the set of all summaries is a finite set. So even if there's infinitely many ways to pop the symbol that we just pushed, the set of summaries that we can collect from them is actually a finite set. In fact, we identify with a summary all the possible plays that have the same effect on the configuration and the winning condition. And when we play our finite game, it is not important which of the sequences we simulate, because the effect for configuration and winning condition are absolutely equal. So let's have a look at the finite game that results from these ideas. So what we wanted to do is we want to remove the stack, store only the top of stack symbol at all times, and store some additional information, and we need to identify what this is. At the meantime, we want to simulate with a finite game the original pushdown game. Now let's assume we already simulated it up to a certain position, a pushing transition that was chosen by some of the players. What we do next is we hand over the control to Eve, so she can propose any subset of the set of summaries. Really any subset she likes. Of course, the idea is that she proposes the set of summaries for which she has a strategy, and she also plays that strategy. So when we remember the image from the previous slide, this is precisely the area of all the summaries that she can produce within her strategy. Then Anna will be the pathfinder, in that she can choose any summary that is inside of the set, and then when she chose one, we will make visible the effects, so the maximal priority ones, and after that the play can continue as if we played one of the sequences, the summary, the effects stored in the summary fits. Now, of course, it is not like all of the plays that occur after the push have to pop the top of stack symbol. So what Anna can do as well as the pathfinder, she can also just push the symbol. What that does is we forget the old top of stack symbol and we remember the new one after the push, and then we continue playing as if we only have the top of stack symbol ready. But what can happen now is, of course, we can run into popping scenarios, right? We can run into the pop, maybe a pop that is what is included in the set of summaries, or we can run into a pop such that the summary was not included of this sequence we have seen in the play. And now, when we run into a popping situation, we may need to make sure that the right player wins. And what I mean by that is that Eve either did not suggest enough summaries, if we run into a summary, into a pop which such that the sequence in between is not captured by any summary in her proposed set, then she made a mistake, because her strategy obviously did not do what she suggested it did. And on the other hand, Anna is misplaying if the game runs into a popping situation where the summary was actually included, because then she could have just chosen the path where she jumps to the summary. So what we need to do is we need to store the set of summaries that was proposed by Eve in our state space. However, this is not quite enough. When we run into the popping situation, we want to check the current summary of the sequence we've played after the push to the set of summaries that was compared. But a single summary also contains the maximal priority that we have seen. So after the push, we have to remember the maximal priority that we have seen since the push of that top of stack symbol. And then when we run into the popping situation, we just have to look at our position, look at the state, look at the maximal priority, and check whether it is, this summary is contained in the set of summaries that were proposed by Eve. And then we let Eve win if this is the case, and we let Anna win if it is not included. Okay, let's recapture what we did in a more abstract way. We try to remove the stack by storing only the top of stack symbol. And in order to make the finite game work, we also had to store the set of summaries that were proposed for that top of stack symbol. And we also need to track the summary since we have seen the last change of the top of stack symbol. And with that, we can actually simulate the original game. Now for the multi-pushdown system, we want to do exactly the same. So we store for each stack the top of stack symbol, we store for each stack the summary since we pushed the symbol, and we store for each stack the set of summaries that were proposed for that symbol. And then the finite game is pretty much the same. We check against a summary when we run into a pop, and when we run into a push, Eve will suggest a new set of summaries. Now what changes is the shape of the summaries. And what we also will see is that the major factor for the size of these finite games is actually the size of the set of all summaries. Because Eve can choose an arbitrary subset, we need to include all the subsets into the state space. Okay, how does summarization work for our two-stack multi-pushdown systems? Now again, we have a strategy for Eve, and we have a play within her strategy. Now, of course, we have a two-stack multi-pushdown system. Parts of this play act on the second stack, and parts of this play act on the first stack. Consider a push-pop pair of the second stack. Now, thanks to the orderedness condition, we know that the second stack must be empty at the moment of the pop. And this very much helps us when trying to understand what the effect of the sequence between the push and the pop is. Okay, so let's capture the effect of the sequence between the push and the pop. The configuration, okay, second stack must be equal because we have a push-pop pair, and as we just said, thanks to the orderedness restriction, it must be that the first stack must be empty. And we have seen before that the state is part of the summary, and the priority also is part of the summary. And actually, we do not need anything else. The effect is precisely that. The state changes, the first stack must be empty, and the maximal priority seen is important. However, we do not have to store that the first stack empties in our summary because this is true for all summaries that exist. So the set of summaries will actually be precisely the same as the set of summaries for a single stack multi-pushdown system. And with this idea in mind, let's again look at the finite game. So we were able to simulate the game previously, maybe some execution on both stats, and then at some point stacks 2 wants to make a pushing transition. Again, we go to an intermediate state where Eve proposes any subset of S2, just as in the case for single stack pushdown systems as we have seen before. And then Anna will do the pathfinding. And the only interesting thing that is now interesting is how do we handle a popping situation. And when we look at which information we store in our state space, we will see that we can easily just check against S2. We have the state and the maximal priority that we have seen since the push on stack 2, the last push on stack 2, in our state space, and the set of summary proposed for it. And so we can just check whether the current play has a summary which is contained in the set of proposed summaries. Okay, that was summarization for stack 2. How does summarization for stack 1 push-pop pairs work? Let's have a look. Okay, so we have another computation and we have a push-pop pair for stack 1. And I already labeled them 1 because we will have a few more push-pop pairs. No, only one more or less, but okay. Again, we want to capture the effect. So let's concentrate on the effect on the configurations first. We have the top configuration before the push and the bottom configuration after the push. Now, because there is a push-pop pair on stack 1, we have equality of the first stack. And as we've seen in the previous two constructions, of course, the state changes, and we probably need for the winning condition to track the maximal priority seen during the whole sequence. Okay, however, something changes here, because in this case, we do not have the orderedness restriction that says that the stack 2 would be empty. Instead, stack 2 can actually push a symbol in between. There might be a sequence of stack 2 operations in between where we have a push, just as we can see in the image. Now, in that case, what has happened is the top of stack 2 symbol has actually changed. So when we look here, this might be another symbol than at the moment of push 1. So we better put it in our summary for the pop 1, for pop 1. Now this is actually the whole effect for the configuration. But our summary has to contain a few more things, because our finite state game, when we try to skip from the push 1 to the pop 1, still we need to be able to construct a complete finite state position. And in a finite state position, whenever we have a top of stack symbol, we also store the maximal priority scene, so the summary for this top of stack symbol. And we store a set of summaries for that top of stack symbol that should be the proposed set from Eve. Now we don't have that here yet, because we did not actually execute the push on stack 2 if we skip from push 1 to pop 1. So instead what happens is we need to enrich our summary so that Eve proposes this information for the skip play, because it is part of the skip play. Okay, so she needs to include in the summary the maximal priority scene since the push on stack 2. So far so good. And she needs to propose a set of summaries. Now the question is, what is the set of summaries she should propose? The first thing that comes to mind is probably this set. The set of all summaries that can occur after the push of stack 2. However, this is not quite correct. When we look at the summarized play, it is actually fixed up to the pop 1, which we see. So it might be that there are popping scenarios which cannot occur at all anymore after we are done with our fixed play. So instead, what we want as the set of summaries, we want to look at this set of plays that are possible, and now we want to catch all the summaries that are possible. Okay, and this is something that slightly got missing in the previous construction. Okay, with this we have the set of summaries for stack 1, which consists of the state space, the priorities for both stacks, the top of stack symbol for the second stack, and a subset of all the possible summaries for the second stack. So how does a finite game look when we have a pushing transition on stack 1? Well, again, Eve will just suggest any subset of the stack 1 summaries. And then Anna again pathfinds, and the interesting situation is again what happens when we actually run into a pop. So what happens is we look at the current position and we look at all the information that we will see. The first information, of course, is the state and the maximal priority seen since the push on stack 1. Those have to coincide. Now what also has to coincide is the top of stack symbol for stack 2 and the maximal priority seen for the since the push of stack 2. So far, so good. The only thing that is not so easy is the set of summaries for stack 2. Now, immediately from an immediate view, I would expect that S2 has to be the set that is part of the summary. But this is not true, because when we look at this and we run into the popping situation here, it is the case that we actually did execute the push and that Anna pathfinded, yes, we want to do the push. And at the moment we did the push on stack 2, Eve did not yet know that the rest of the sequence would end in this push on stack 1. So she would actually have proposed this set S2, because there might have been a play where this pop on stack 1 would not have happened, and we have another way of popping stack 2. However, in our summary, we have the smaller set, right? Where we fixed already the play up to the pop on stack 1. So what we want to check instead is whether there is a summary where the set of summaries for stack 2 is included in this set S2.